Dr. Sage here. Today we're going to discuss Chapter 3. Chapter 3 is an entire chapter where we talk about water. Now water is a very small, simple molecule, so why would we spend an entire chapter learning about the water molecule? Well, because this is biology, the study of living things, and it turns out that all living things need water in order to live. We could not have life on this planet if it weren't for all of the water on this planet. Also, all living things on this planet are made up of cells, and cells are surrounded by water, and cells are made up of between 70 and 95% water. So all living things need water in order to live, and all living things are mostly made out of water. So that's why we're going to spend a chapter learning about water. Now, as we discussed in Chapter 2, the chemistry chapter, we talked about the fact that water is a polar molecule. As a quick refresher, remember what that means is that the bonds between oxygen and hydrogen are covalent bonds, which means they're sharing a pair of valence electrons. But more specifically, they're polar covalent bonds, which means they're unequally sharing their pair of valence electrons. So the electrons end up with oxygen more often than they end up with hydrogen. Because of that, the oxygen ends up building up a partial negative electrical charge, and the hydrogens end up building up a partial positive electrical charge. So that water molecule is a polar water molecule. Now we also discussed that the partial negative on one water molecule is attracted to the partial positive on another water molecule, and that creates a bond called a hydrogen bond. And because of that, water is attracted to other water molecules. Now, what I did not talk about last time is the fact that one water molecule does not form a hydrogen bond with just one other water molecule. Like you can see in this figure here, this water molecule in the center has hydrogen bonds to 4 other water molecules. Okay, so it turns out that water forms lots of hydrogen bonds with water. And as kind of a preview for this chapter, there's going to be 4 properties of water that allow life on this planet. And it turns out that all of those properties are because of these hydrogen bonds. So actually, we couldn't have life on this planet if it weren't for these hydrogen bonds. And you'll see how that is as we go throughout this chapter. So the 4 properties of water that allow life on the planet is first the fact that water is cohesive, which means it sticks to itself. Second, the fact that water can moderate temperature. Third, the fact that water expands whenever it freezes, or another way of saying that is that ice floats. And fourth, the fact that water is a very good solvent. So we're going to go through these 4 properties one at a time, starting with the cohesive behavior of water. Okay, now what it means that the water is cohesive means water sticks to itself. Why is that? Because of the hydrogen bonds. So this water molecule is attracted to this water molecule because of a hydrogen bond, and this one, and this one, and this one. So water molecule is cohesive, meaning it sticks to itself because of the hydrogen bonds that water forms with other water molecules. That actually allows us to have life on this planet. We couldn't have life on this planet if it weren't for the fact that water sticks to itself, the fact that water is cohesive. Why? Because all living things on this planet need plants in order to live. Because you are either a plant that directly makes your own food, glucose, sugar, through the process of photosynthesis, or you're an animal that eats a plant that made the food, the glucose, through the process of photosynthesis, or you're an animal that eats an animal that ate a plant. So the original source of all of our energy, all of our food for the living things on this planet is coming from plants. And it turns out that plants could not live if it weren't for the fact that water is cohesive. So here's an example of a plant. And what happens is the plant is taking water in through its roots, and the water is traveling through the plant from the roots all the way to the leaves, and then the water is exiting the plant from the leaves. So the liquid water is evaporating and becoming water vapor in the air around the plant. And plants need water to travel through them in order for the plant to live. Okay, if water was not traveling through this plant, then this plant could not live. Okay, kind of like you need blood to travel throughout your body in order for you to live. Okay, but how do you get blood to travel through your body? You have a muscle called your heart that pumps your blood throughout your body. Okay, well, it turns out plants do not have muscles. So since this plant doesn't have a muscle like your heart, it can't pump water. So if that's the case, then how is water traveling through this plant without a muscle to pump it? Okay, well, let's say we take one of these leaves and we, magnify that leaf, and what we're going to see is there's going to be liquid water molecules inside that leaf of the plant. What's going to happen is that liquid water molecule is going to evaporate. It's going to turn from liquid water inside the leaf of the plant to water vapor in the air around the plant. Well, this water molecule, this one that's leaving the leaf, is hydrogen bonded or cohesive to the one behind it. So when this one exits the leaf of the plant, it takes this one and pulls it up into its spot. Well, that one's hydrogen bonded or cohesive to the one behind it, so it pulls it up into its spot. That one pulls that one up into its spot. So basically, you have a long chain of water molecules from the leaves all the way down to the roots. And whenever one exits the leaf of the plant, it pulls this whole chain up one spot. So the way that water travels through the plant is because of the fact that water is cohesive. If it weren't for that, then plants could not live. And without plants, we wouldn't be able to live on this planet because we wouldn't have a source of food. Now, besides water being cohesive, which means it sticks to itself, water is also adhesive, which means it can stick to other things. And we'll talk a little bit about that later. Okay, and you can actually see for yourself the fact that water is cohesive. Go get a glass and fill it all the way up to the top of the glass, the lip of the glass, with water. And then just add a little more water. When you do this, what's going to happen is that water is going to bubble up over the lip of the glass, the rim of the glass. It's not going to spill out of the glass. So what's happening is those water molecules are being cohesive. They're holding on to each other. They're pulling on each other strong enough to overpower the force of gravity. Now, yes, if you add more water, then the water will spill out of the glass. But if you add just a little bit, due to the cohesive behavior of water, it will pull on itself strong enough to overpower the force of gravity. Another way you can see this is by looking at a water droplet on a leaf. So this water droplet in this leaf here, what's happening is gravity is trying to pull this water down. Gravity wants this water to lay flat on the leaf. But this water is not laying flat on the leaf. What happens is it's kind of bubbling up on the leaf. The reason is because the water is pulling on itself, and it's pulling on itself strong enough to overpower the force of gravity. Some organisms even use the fact that water is cohesive to help them to live. For example, this organism here, this water strider, can actually walk on water. Because the fact that water is cohesive, it creates a tension on the surface of the water called surface tension. And that's a tension, a force that's actually strong enough for this organism to walk across the water. Okay. The second property of water that allows life on the planet is the fact that water can moderate temperature. Now, in order to explain that, I need to actually explain a little bit more about energy and about temperature, like what temperature actually is. Because it turns out temperature is not actually like I feel hot or I feel cold. What temperature actually is it's measuring how fast molecules are moving. Okay, if you have an object and it's cold, what happens is its atoms are moving. If it's a solid object, the atoms are just vibrating next to each other, but they are moving. Okay, now you take the cold object and you heat it up. What happens is those molecules move a lot faster. Okay, so what temperature is actually doing is it's measuring how fast atoms are moving. So a higher temperature means the molecules are moving faster. Lower temperature means the molecules are moving more slowly. Okay, and this also relates to energy, because we talked in a prior chapter about different types of energy. One type we talked about was potential energy, which is energy that's stored, energy that can later be used to do work. Another type of energy is called kinetic energy, which is the energy of motion. Anytime something is moving, it has kinetic energy. So heat, or temperature, is a measurement of kinetic energy, because temperature is measuring how fast atoms are moving, so that's movement. It's a movement of atoms, but it's still movement, so it's a type of kinetic energy. Okay, and we want to have a way of measuring the amount of energy something has and a way of measuring temperature. Okay, you're used to measuring temperature using the Fahrenheit scale in the United States. In science, we don't use a Fahrenheit scale. We would use typically the Celsius scale. Now, technically, Celsius is not the official unit of temperature for science. Technically, the official unit of temperature for science is Kelvin, but we're not going to use Kelvin in this class, and another chapter might explain why we can use Celsius instead of Kelvin. Okay, but we're going to use the Celsius scale to measure temperature. Now, to start getting you used to Celsius, some common temperatures you might interact with a Celsius scale. Okay, the temperature that water freezes at is 0 degrees Celsius. The temperature that water boils at is 100 degrees Celsius. Okay, so the Celsius scale is related to water. It's related to the temperature that water freezes, 0 degrees Celsius, temperature that water boils, 100 degrees Celsius. Another temperature that you need to get used to is human body temperature. Because human body temperature is not 98.6 degrees, because you don't use Fahrenheit anymore, you're now using Celsius. So human body temperature is 37 degrees Celsius. That's human body temperature. Okay, so that's the Celsius scale. Now, we do also want to be able to have a unit of measurement for energy. And there's different units of measurement for energy, just like you can measure distance in inches or feet or meters or miles or kilometers. You can measure energy in a unit called a joule, which we're not going to use in a biology class. You'll use that in like a physics class. Or another unit of measurement for energy is called a calorie. And you've actually heard of calories before, because you've heard of them in terms of your food. Like if you read your food label, say like that donut has like 300 calories in it. What that's telling you is how much energy is stored in that food, like that donut. The reason we eat is not just because we're hungry, we eat because we need energy. Okay, your food that you're eating is storing energy. How much energy the food is storing is measured in how much calories that food has. The higher the calories, the more energy it's storing. The lower calories, the less energy it's storing. Okay, so calorie is a unit of measurement of energy that we're going to be using in a biology class. Now, there is a more technical definition for calorie, and it does also relate to water and temperature, things we're talking about today. But we're not going to get bogged down into details today of that definition of a calorie. So back to the second property of water that allows life on the planet. That is the fact that water can moderate temperature. Now, to explain that, what I have to have you understand is the fact that different substances need to absorb a different amount of heat energy before they'll raise their temperature. Alright, so let me give you an example. Let's say you're at home, it's a sunny summer Florida day, and you go and you step outside, and let's say you have a wooden deck outside, and you're barefoot and you step on that wooden deck. Okay, well that wooden deck is warm on your feet. Now you step off of your wooden deck and step onto your concrete driveway, and that concrete driveway is very hot. Now, the wooden deck and the concrete driveway receive the same amount of heat energy. They were both in the same amount of sunlight for the same amount of time. But the concrete raised its temperature much more than the wood did of the deck. Okay, so it's too hot out there, so you go back inside. You're going to cook something, and you got a pot of water on your stove that's you're going to start boiling something, and you're stirring that water with, for some reason, 2 spoons at the same time. One of them is a wooden spoon, one is a metal spoon. Okay, and you step away for 5 minutes, you come back, you go to grab those spoons. That wooden spoon is not really hot. That metal spoon is really hot. Now, both of those spoons were in the same temperature water for the same amount of time, but the wooden spoon did not raise its temperature as much as the metal spoon did. Okay, so different substances need to absorb a different amount of heat energy before they will raise their temperature. The technical definition of this is it's called specific heat. Specific heat is the amount of heat energy that something must absorb before it will raise its temperature. Again, there's a more technical definition, but that's basically what it means. Now, it turns out that water needs to absorb a lot of heat energy before it will raise its temperature. In other words, water has a very high specific heat. Water is more like the wooden spoon, not like the metal spoon. Water needs to take in a lot of heat energy before its temperature will raise. It turns out that that allows life on the planet. We could not have life on the planet if it weren't for the fact that water has a very high specific heat. Well, let me give you an example. Let's say that we're looking at a coastal region. This is California, but you can see the same thing in Florida. Okay, now all of this area is all receiving the same amount of heat energy. The sun is shining on all of this equally, same amount for the same amount of time. However, the water does not raise its temperature as much as the solid earth. This is like the wooden spoon, and this is like the metal spoon. Even though they're both receiving the same amount of heat energy, this raises temperature much faster than this does. And the closer you get to that large mass of water, the lower your temperature is going to be. Why? Because that large mass of water is absorbing all of that heat energy that's coming from the sunlight. Now that's just a small coastal region, but imagine our planet. Our planet is covered with a large mass of water, our oceans. What happens during the daytime, we're receiving a lot of heat energy. Where is that heat energy going? Where most of it is going is to the oceans. It's going to these large masses of water. Those oceans, those large masses of water, absorb all that heat energy without raising their temperature very much. What does this do? This keeps our planet cooler than it would be otherwise. If we did not have the large masses of water covering our planet, if we didn't have our oceans, what would happen during the daytime when the sun is shining? It would get too hot. Because you wouldn't have those large masses of water to absorb all that heat energy, so the planet would get too hot. It actually would get too hot for you to live. You die from heat. Now, what happens at night? At nighttime, the exact opposite happens. At nighttime, when the sun is not shining, okay, we're not receiving all that heat energy, so during the nighttime, the temperature starts to drop. The temperature decreases in the nighttime compared to the daytime. But it does not get too cold for you to live. Why? Because those large masses of water that absorbed all that heat energy during the day, they release the heat energy back to the environment at night. In other words, it keeps it warmer than it would be otherwise at night. So if it weren't for all the water covering our planet, then during the daytime it would be too hot for you to live, you die from heat. During the nighttime it would be too cold for you to live, and you die from the cold. But because we have all the large masses of water covering the planet, it allows us to live on this planet. Because it keeps our planet at a fairly narrow temperature range, a temperature range we can actually live at. Why is that? Because water has a very high specific heat. Why does water have a very high specific heat? Again, it has to do with the hydrogen bonds. Okay, remember what I said a higher temperature actually means. What a higher temperature actually means is the molecules are moving faster. So if I want the temperature of this water molecule to heat up, what has to happen is that water molecule has to start moving around faster, has to start moving around more. Okay, well, in order for this water molecule to start moving around faster, moving around more, what it has to do, it has to break all of these hydrogen bonds so that it can actually move around more. Okay, well, it turns out it takes energy to break chemical bonds like hydrogen bonds. So the reason that water has a very high specific heat is because it has to take in a lot of heat energy to break the hydrogen bonds so the water can start moving around more, which remember means higher temperature. So that's the second reason that water allows life on this planet, because it keeps the temperature of our planet at a fairly narrow range, a range that we can actually live at. Why? Because water has a very high specific heat. Why does it have a high specific heat? Because of all the hydrogen bonds that water forms. Now, a term that's related to specific heat is heat of vaporization. That's the amount of heat that something must absorb before it can turn from its liquid form into its gas form. Okay, so for example, turn from liquid water into water vapor, the water that's in the air around you right now. It turns out that water also has a very high heat of vaporization. Why? Again, because of all the hydrogen bonds that water forms. But the fact that water has a high heat of vaporization allows organisms like us to more easily live on this planet. For example, let's say you go outside and you start to go for a run in a sunny Florida summer day. Okay, what's going to happen? One of the first things that's going to start happening is you're going to start sweating. Okay, your body is doing that intentionally. What your body is doing is it's putting a layer of liquid water on your skin. Now that liquid water on your skin, your sweat, is going to evaporate. It's going to turn from liquid water on your skin to water vapor in the air around you. But in order to turn from liquid water, your sweat, into water vapor in the air around you, it has to absorb a lot of heat energy. Okay, and that heat energy has to come from somewhere. Where it comes from is it comes from you. So your sweat, the water on your skin, absorbs your heat energy to get turned from liquid water to water vapor. In other words, it cools you down. Makes it easier for you to do things on this planet. Okay, if we didn't sweat, then we'd have more people getting heat strokes and having problems doing things whenever it was warm outside. So the third property of water that actually allows life on this planet is the fact that ice floats. It's actually very weird that ice floats. We just don't think of it as being odd or weird because we're used to seeing it all the time. Okay, well, ice is a solid form of liquid water. For most substances, not water, but most every other substance, the solid form is more dense than the liquid form, so the solid would sink underneath the liquid. But that's not what happens with water. With water, solid water, which is ice, is less dense than liquid water, so ice actually floats on top of liquid water, which is very odd, but it allows life on this planet. But before I can explain to you why the fact that ice floats allows life on this planet, I need to first explain to you why ice floats and why it's abnormal that ice floats. In order to do that, I first need to very briefly explain to you a little bit about three of the states of matter, which is solid, liquid, and gas. And how I'm going to explain that to you is through a very, very sad little states of matter dance. In a solid, what happens typically in a solid is the molecules are very close together and they're just vibrating next to each other. Okay, so that's my solid dance. Now, you take that solid and you heat it up. Remember what heating it up really means is you speed up the molecules. So you go from a solid, where they're vibrating next to each other, to a liquid, where they're moving around each other. Okay, so that's my liquid dance. Then you take that liquid and you heat it up even more. Remember what that really means is you speed it up even more. And it'll go from a solid to a liquid to a gas, where they're moving very fast and they're very far away from each other. And that's my gas dance. And as sad as that is, that's the best dances I can do. Okay, so in the gas form of water, water vapor, like the water that's in the air around you right now, those water molecules are moving very fast. That's what these lines are supposed to represent. And because they're moving so fast, they're very far away from each other, and they don't form hydrogen bonds with each other. Now you take water vapor, the gas form of water, and you cool it down. Remember what cool it down really means is it means slow it down, and it will turn from the gas form into liquid water. Now, as you cool it down, as you slow it down, those water molecules then get close enough, and they're moving slow enough to form hydrogen bonds with each other. You cool it down even more. Remember what cool it down really means is it means slow it down. And what should happen is those molecules should get even closer together. But that's actually not what happens with water. Because what happens with water is as you cool it down, as you slow it down, those water molecules can start forming very rigid hydrogen bonds. Now, hydrogen bonds have to be a certain distance, like the molecules have to be a certain distance away from each other to form those hydrogen bonds. And because of the unique shape of water, that V shape, and remember it forms more than one hydrogen bond, like this water molecule here is forming like 4 hydrogen bonds with 4 other water molecules. Because of the shape of water, and because of all the hydrogen bonds it forms, what happens is these water molecules end up forming this rigid crystal lattice structure. And because of that, the water molecules are farther away from each other in solid water, ice, than they are in liquid water. In liquid water, they can get closer together than their hydrogen bonds would allow. So what's happening in solid water, ice, they form these rigid hydrogen bonds and they kind of lock into place. In liquid water, they are forming hydrogen bonds, but what's really happening, since it's a higher temperature, they're moving faster, they have more kinetic energy, so these water molecules are moving close to each other. They get close enough to form a hydrogen bond, but then they can move too close for that hydrogen bond, and that hydrogen bond can then actually break. They can move closer than a hydrogen bond would allow. And that's what these little kind of explosions are representing, the making and breaking of hydrogen bonds. Okay, so because of that, in liquid water, the water molecules are closer together than in solid water, ice. Because of that, in solid water, ice, it's less dense, so it floats on top of liquid water. So, because of that, ice floats. And that actually allows life on this planet. Because a lot of places on this planet, certain times of year, it gets cold enough for water to freeze. Not in Florida, but in a lot of other places, it gets cold enough for water to freeze. What happens is the cold air up here starts cooling down the liquid water. Okay, and because the fact that solid water ice is less dense than liquid water, what happens is that layer of ice forms on the top of, let's say, this lake here. Okay, well, once you form a solid layer of ice on the top of the lake, what happens is this actually acts as like an insulator, like a barrier. And it prevents the cold air up here from getting to the liquid water down here. So because of that, the lake does not continue to freeze, and it does not freeze solid, killing everything inside it. If water was like most other substances, what would happen as the cold air was cooling it down, it would start to turn into its solid form. But if it was like most other substances, the solid form would be more dense, so the ice would form at the bottom of the lake. Then you wouldn't have this isolating barrier at top, the insulator, so the cold air could keep cooling it down. What happened is the lake would freeze from the bottom all the way to the top, freezing solid and killing everything that lived inside that lake. But that doesn't happen because ice floats. Why does ice float? Because solid water is less dense than liquid water. Why is that? Again, because of all the hydrogen bonds that water forms. So that's the third property of water that allows life on the planet, the fact that ice floats. The fourth property of water that allows life on the planet is the fact that water is a very good solvent. But to explain that, first there's some terms you're going to need to know. So a solution is a liquid that is a homogeneous mixture of substances. A solvent is the dissolving agent of a solution. The solute is a substance that is dissolved. Alright, so let me give you an example. Let's say, again, you're at home, you're in your house, you have a glass of water and you pour some sugar in it, okay, and then that sugar dissolves in the water, so it will turn invisible, you won't see it, and then that makes sugar water. I guess because for some reason you want to drink sugar water instead of drinking water. So in that example, the sugar is the solute, the thing that is dissolved. The water is the solvent, the thing that's doing the dissolving, and the sugar water solution is the two combined together. Now, water is not the only solvent. There's lots of different types of solvents, but since this is a biology class, not a chemistry class, we're going to focus on water being the solvent. Okay, so an aqueous solution is one in which water is the solvent. This term aqueous is referring to water, so a water solution. Okay, so many things very easily dissolve in water. Why? Again, because of the hydrogen bonds. Because of the fact that water is a polar molecule. So for example, let's say you're in your house again, you're sitting at your dining room table, and for some reason you're playing with your table salt. I don't know why, I guess you're bored, waiting for your food, so you're just sitting there playing with table salt. So you take that table salt and you try to take one of those crystals of table salt and you try to crush it between your fingers to break it into smaller pieces. I guess you're angry that your food's not here yet. You're taking it out on the salt. But as you're trying to crush that salt crystal into smaller pieces, you're probably not going to be able to. Because you are not physically strong enough to break that salt crystal apart. Now, yes, you could put it on the table and take a spoon and crush it up with a spoon, but just using your fingers, you're not going to break apart that salt crystal. Now, take that salt crystal that you were not physically strong enough to break apart and just drop it in a glass of water and don't do anything else. What will happen? The water will instantly start dissolving that salt crystal. The water will start to break apart that salt crystal, the thing you couldn't break apart. Okay, why? Because water is a very good solvent. Why is that? Remember, table salt, sodium chloride, is an ionically bonded compound. So it's made up of negatively charged chloride ions, positively charged sodium ions. Water is a polar molecule. So what happens is the partial positive charges on the hydrogen atoms are attracted to the full negative charges on the chloride ions, and they're actually attracted strong enough that it rips this chloride ion away from the salt crystal. Similarly, the oxygen atoms are going to have partial negative electrical charges, which are attracted to the full positive electrical charge of the sodium ions, and they're attracted strong enough they rip that sodium ion away from the salt crystal. Okay, so water is ripping apart the salt crystal, it's dissolving it. Okay, why? Because water is a polar molecule, because it forms lots of hydrogen bonds. Because of that, water is a very good solvent. Now, even very large molecules, like sodium ions, chloride ions are very small, but even very large molecules can very easily dissolve in water. For example, this purple blob here, okay, that represents a protein. We're going to learn about them later in the semester. But basically, your cells are filled with proteins. Basically, everything your cells needs done are done by proteins. And your cells are mostly made up of water, like 70 to 95% water. So those proteins have to be able to dissolve in the water of your cells, which they do very easily because those proteins are going to have some partial negative and partial positive electrical charges because they will have some polar covalent bonds, which those partial negative and partial positive electrical charges are attracted to the partial positive and partial negative charges on water. So because of that, the protein very easily dissolves in water. And many things will very easily dissolve in water. Take salt. Drop it in a glass of water, it will very easily dissolve. Take sugar, drop it in a glass of water, it will very easily dissolve. Like you got a pot of water on your stove because you're going to cook something, you pour some salt in it, the salt very easily dissolves in that pot of water. Now, that same pot of water, you take some oil and pour the oil in the water. The oil does not easily dissolve in the water. Oil and water do not mix. The oil stays floating on top of the water. So some things will very easily dissolve in water and other things will not. So of course there's names for these. Those are called hydrophilic and hydrophobic. A hydrophilic substance is one that has an affinity for water. So something that will easily dissolve in water. A hydrophobic substance is one that does not have an affinity for water, so something that will not easily dissolve in water. These names are actually telling you what they mean, okay? So hydro, that means water. Phobic, you've heard that before, at least something similar, like you've heard of a phobia, which is like a fear. So technically, hydrophobic means something that's afraid of water. So that's something that does not easily mix with water, does not easily dissolve in water, like oil. Okay, hydro means water, philic means loving. So this is something that loves water, so will easily dissolve in water, like sugar or salt. So things that are hydrophilic are things that are going to have some type of electrical charge to them. So ions, like a sodium ion, is going to be hydrophilic, or a chloride ion is going to be hydrophilic. Okay, because these charges are attracted to the partial charges on water. Or polar molecules, okay, like glucose, which is sugar, your cell's preferred source of energy. Glucose is a polar molecule, so it's going to have some partial negative and partial positive electrical charges. Well, those partial negative or partial positive electrical charges are attracted to the partial negative and partial positive electrical charges on water. So glucose will very easily dissolve in water. So things that are hydrophilic are ions and polar molecules. Things that are hydrophobic are things that do not have an electrical charge. So those are going to be non-polar molecules. Okay, so oil is hydrophobic because it's made up of non-polar bonds. It's a non-polar molecule. Most biochemical reactions occur in water. All right, so what exactly does that mean? Okay, your cells are mostly made up of water. They're like 70 to 95% water. And what your cells essentially are is they're just bags doing chemical reactions. Okay, everything your cells do is a chemical reaction. Moving a muscle is a chemical reaction. Thinking is a chemical reaction. Building DNA, building proteins, those are chemical reactions. Your cells are doing literally millions of chemical reactions every single second. And those chemical reactions are happening inside your cells. And since your cells are mostly made up of water, 70 to 95% water, those chemical reactions have to be able to happen inside water. So that's what it means by most biochemical reactions occur in water. Chemical reactions depend on collisions of molecules and therefore on the concentration of solutes in an aqueous solution. So what that is saying is, let's say you have two chemicals, chemical A and chemical B, and they're going to react with each other to form chemical C. Well, in order for chemical A and chemical B to react with each other, first what they have to do is they have to collide with each other. They have to run into each other. Okay, if they're not near each other, they can't react with each other. Alright, so here's an analogy. Let's say you're in your room right now, and you and two other people are just randomly walking around the room. So not paying attention where you're walking, just randomly walking around your room. Okay, so if the three of you are randomly walking around the room, once in a while you're going to bump into somebody. Whenever you bump into somebody, that's going to represent a chemical reaction. And as the three of you are randomly walking around your room, once in a while you will bump into each other and do a chemical reaction. But now let's say, instead of the three of you in that room, let's say I put 30 of you in the same size room. Ask you to randomly walk around the room. What's going to happen then? Well, you're going to bump into each other a lot more often. In other words, the more of you there are in that certain size space, the more often you're going to bump into each other, or the more often you're going to do chemical reactions. Okay, so the concentration, the amount of chemicals within a certain size space, determines how fast chemical reactions can happen. And you need your chemical reactions to happen very quickly. Like I said, literally millions per second. They have to happen that fast in order for your cells to live. So we care about how many of the molecules there are inside your cells. But there's lots of them. There's an enormous number of them. Because they're so tiny, there's a number that's almost impossible to comprehend how many there are. So we're going to be working with very large numbers. But frankly, it's very difficult to work with very large numbers. So to make it easier, what we want to do is we want to use a word to represent a number. And at first, this sounds confusing, using a word to represent a number. But if you think about it, you already do this in your daily life. You use the word dozen. Okay, you know that dozen means 12. That's what dozen means. So you're using a word to represent a number. A dozen means 12. And the word is not specific to the item. Like you could have a dozen donuts, or a dozen eggs, or a dozen bowling balls. Okay, dozen just means the word 12. So we're going to use a word to represent a number. Now, the number is going to be a very large number. Okay, but it's just a number. And the word is called a mole. Okay, so a mole of something is when you have 6.02 times 10 to the 23rd numbers of something. That's 1 mole. Okay, so if you have 1 mole of something, you have 6.02 times 10 to the 23rd numbers of something. Okay, so this is an enormous number. Now, if you're not real familiar with this way of writing numbers, basically what that means is 6 with 23 zeros after it. Okay, so that's a huge number. Like, for example, if I were to say 6 million, that would be 6 with 6 zeros after it. Okay, this is 23 zeros after it. So this is an enormous number, but it's just a number. Sometimes you'll hear it called Avogadro's number, named after the scientist who discovered it. When you have 1 mole of something, you have 6.02 times 10 to the 23rd numbers of something. And it's not specific to the item. Just like a dozen could mean a dozen donuts, a dozen eggs, a dozen bowling balls. Okay, if you have 1 mole of something, you have 6.02 times 10 to the 23rd numbers of something. Like if you have 1 mole of sodium ions, well, you have 6.02 times 10 to the 23rd numbers of sodium ions. If you have 1 mole of carbon atoms, well, you have 6.02 times 10 to the 23rd numbers of carbon atoms. If you have 1 mole of oxygen atoms, you have 6.02 times 10 to the 23rd numbers of oxygen atoms. Okay, so it's not specific to the item, it just means that number. It's an enormous number, but it's just a number. Okay, so that's what a mole is. A mole does also relate back to the periodic table. So in the last chapter, we talked about the periodic table. And I taught you inside each box, there's a set of information. So for example, sodium, inside the box we have 11 Na23. Okay, so that's what it says inside the box of the periodic table for sodium. I told you the number at the top, that's the atomic number, that's the number of protons it has. It's also the number of electrons it has. The number at the bottom is the number of protons plus neutrons added together. So 23 minus 11 means you have 12 neutrons. I also told you this number at the bottom represents how much one single atom weighs. So one sodium atom will weigh 23 Daltons, or 23 AMUs. Remember, that means the same thing. Okay, so this number is how much one single atom weighs in units of Daltons. Now, if you take the same number, so this 23, and use a different unit of measurement for mass, instead of Daltons, we use grams, then that's how much 1 mole of sodium atoms will weigh. So this number at the bottom means two different things at the same time. If it's in units of Daltons, that's how much one single sodium atom weighs. If it's in units of grams, that's how much 1 mole of those sodium atoms will weigh. So 1 mole of sodium atoms will weigh 23 grams. Okay, in contrast, if we look at the periodic table for hydrogen, okay, the number at the bottom is 1, so 1 mole of hydrogen atoms will weigh 1 gram. Okay, so this number at the bottom represents how much one atom weighs in Daltons, or how much 1 mole of those atoms weigh in grams. Now, the voodoo for how this same number can be used for two different things with two different units, take chemistry to learn that. Just accept it for this class. Now, if you notice, mole is a number. So if I have 1 mole of hydrogen atoms, I have 6.02 times 10 to the 23rd numbers of hydrogen atoms. If I have 1 mole of sodium atoms, I have 6.02 times 10 to the 23rd numbers of sodium atoms. So in both cases, I have the same number of atoms, 1 mole of hydrogen versus 1 mole of sodium. But if you notice, 1 mole of sodium weighs a lot more, 23 grams, than 1 mole of hydrogen. It only weighs 1 gram. Why is that? Because the atoms come in different sizes. Like sodium, 1 sodium atom weighs 23 Daltons, while 1 hydrogen atom only weighs 1 Dalton. So this is kind of like saying, you know, if I have a dozen bowling balls, that's going to weigh a lot more than a dozen golf balls. Why? Because a bowling ball is a lot bigger than a golf ball. So because of that, if I have a dozen bowling balls, it will weigh a lot more than a dozen golf balls. Just like if I have a mole of sodium, it will weigh a lot more than a mole of hydrogen, because each sodium weighs a lot more than each hydrogen atom. Why do we care that we can use this number at the bottom to have the weight for how much 1 mole will weigh? Well, because like I said, we care about the number of atoms or molecules we have in our cells, but they're very small. So you cannot count them. Okay, they're too small to see, so you can't count them. Also, there's too many of them. If you started to count, like right now, like if you started to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you would die before you could get to this large a number. You couldn't count to that big a number. Okay, it's too big. Because of that, we cannot count the number of molecules or atoms. But what we can do is we can very easily weigh out those atoms. Like I can easily get out a scale and weigh out 23 grams of sodium. And since I know in the periodic table it says this number at the bottom is 23, if I weigh out 23 grams of sodium, then I know I will have this number of sodium atoms, 1 mole of sodium. So what we're doing is we're using weight to determine number. So another analogy. Let's say that I have a pile of bowling balls over here, and I need to know how many there are. I need to know the number of bowling balls. But for some reason, I'm too lazy to count them. However, they happen to be sitting on a scale. And the scale says that the pile of bowling balls weighs 120 pounds. Okay, well, if I know that one bowling ball weighs 10 pounds, and I know the pile of bowling balls weighs 120 pounds, then I know I have 1 dozen bowling balls. Okay, so what I'm doing is I'm using weight to determine number. That's the same thing we're doing with moles. If I know that a mole of sodium weighs 23 grams, and if I weigh out 23 grams of sodium, then I know I have this number of sodium atoms. So I'm using weight to determine number. Now, again, let's say I have a pile, but this time let's say I have a pile of golf balls. And again, I need to know how many there are, but again, I'm too lazy to count them. But again, they happen to be sitting on a scale. And it says that that pile of golf balls weighs 12 pounds. Okay, well, if one golf ball, if I know it weighs 1 pound, and the pile of golf balls weighs a total of 12 pounds, then I know I have 1 dozen golf balls. Okay, so again, I'm using weight to determine number. So now, let's say that I ask you to bring me a dozen shoes. Okay, if you bring me a dozen shoes, then you're going to bring me 12 shoes, because remember, a dozen means 12. Now let's say I ask you to bring me a dozen pairs of shoes. In that case, you're going to bring me 12 pairs of shoes, because a dozen means 12. Okay, so I can use this word dozen to refer to a shoe or to a pair of shoes. But if I weigh out a dozen pairs of shoes, then it's going to weigh twice as much as a dozen shoes, right? Okay, so the same is true with using the word mole. Okay, so let's go back to hydrogen in the periodic table. Okay, this is what it says for hydrogen. So if I ask you for 1 mole of hydrogen atoms, then it would weigh out 1 gram. Okay, but now let's say I ask you for 1 mole of hydrogen gas. Okay, hydrogen gas is 2 hydrogens attached to each other by a covalent bond. So if I want 1 mole of hydrogen gas, what you have to do is you have to account for the weight of each atom. This hydrogen weighs 1 and this hydrogen weighs 1. So a mole of hydrogen gas would weigh 2 grams. So this is like a dozen shoes versus a dozen pairs of shoes. It's going to weigh twice as much. So a mole can refer to an atom, like hydrogen atom, or it can refer to a molecule, like hydrogen gas. And this can be used for even very large molecules. For example, table sugar, that stuff you might add to your coffee, is a very large molecule. 1 molecule of table sugar has 12 carbon atoms, plus 22 hydrogen atoms, plus 11 oxygen atoms. So if I want a mole of table sugar, then I have to account for the weight of each atom. So there's 12 carbon atoms, and each one weighs 12. Okay. And there's 22 hydrogen atoms, and each one weighs 1. And there's 11 oxygen atoms, and each one weighs 16, and I'm too lazy to do that in my head. But whatever that comes out to be, you add those 3 numbers together, and it will total up to 342. So if I want 1 mole of table sugar, then I will weigh out 342 grams of table sugar. I'm just accounting for the weight of each of the different atoms that make up that molecule table sugar. Okay, so that's a mole. It's just a word that means a number. Now, to be more confusing, there's a word that sounds like mole, and it's related to mole, but it's not the same thing. It's called molar. Okay, so a mole is a number, while a molar is a concentration. What I really care about is the concentration, not the number. Like, remember back to you know, the 30 of you walking around in your room, and you're going to bump each other fairly often. Every time you do, that's a chemical reaction. I didn't actually care that there was 30 of you. I cared that there was 30 of you in a certain size room. If there's 30 of you in the room you're in right now, you're going to bump each other fairly often. If there's 30 of you randomly walking around Orlando, you're almost never going to bump into another person just by random chance. Okay, if there's 30 of you in that size space. So I don't actually care about the number. I care about the concentration, how many in a certain size space. A mole is a number, while a molar is a concentration. So a 1 molar solution is when you have 1 mole of something in 1 liter of water, since this is a biology class. So this is a concentration, a number in a certain size space. 30 people in your room, okay? That's a concentration. And we care how concentrated our solutions are because it's going to change how the chemical reactions will happen. Okay, so back to water. All right, so not very often, it's pretty rare, but once in a while, something will happen with water molecules. And what will happen is this attraction between this oxygen and this hydrogen, so this hydrogen bond here. Once in a great while, what will happen is this water molecule down here will actually steal this hydrogen from this other water molecule. So this hydrogen is going to go over here. Okay, when that happens, instead of this being H2O, it becomes OH with a negative charge. And then since this one is stealing the hydrogen, instead of this being H2O, it becomes H3O with a positive charge. All right, this OH minus, this is called hydroxide ion. This H3O plus, that's called hydronium ion. Now, why am I telling you this? Because we're talking about water, the chapter on water, and because the next topic we're going to discuss as it relates to water is acids and bases. So it turns out that this hydroxide ion, OH minus, is a base. This H3O plus hydronium ion, it is an acid. And in a few minutes I'll define exactly what is an acid and what is a base, but just for now, you should know that OH minus is hydroxide ion, and it is a base. H3O plus is hydronium ion, and it is an acid. Okay? Now, to make it more confusing, most of the time we actually will not call this hydronium ion, H3O plus. Okay? Most of the time what we're actually going to call that is hydrogen ion, H plus. So we're going to use these two interchangeably like they're the exact same thing. Now why can we do that? Because if you have H plus in water, it will always combine with the water and turn into H3O plus. Okay, so we use these two like they're the same thing because if you put this in water, it becomes this. However, most of the time, we're actually going to call it this. We're going to call it H plus or hydrogen ion. Most of the time, you'll not hear it called hydronium ion. Okay, so use these two like they're the same. So this H plus hydrogen ion, that is an acid. To make it even more confusing, there's a third name we call this at the same time. This is also called a proton. So we're going to use proton to mean the same thing as hydrogen ion. Okay, so why can we use these two like they're the exact same? If you go back and you look at the periodic table for hydrogen atom, it says 1H1. Okay, so what that means is a hydrogen atom has one positive proton and it has one negative electron. And then 1 minus 1 means it doesn't have any neutrons. So a hydrogen atom is just a single proton surrounded by a single electron. That's what a hydrogen atom is. Now if you go from hydrogen atom to hydrogen ion, what happens is you lose this electron. So if this electron's gone, then all it actually is a single proton. So that's why we can call a hydrogen ion a proton, because they are the exact same thing. Okay, so hydronium ion, hydrogen ion, proton, those are acids, and they mean the same thing. Hydroxide ion, OH minus, that's a base. Now, if you have absolutely pure water, so H2O and nothing else, pure water, then it will have exactly equal concentrations of hydrogen ions and hydroxide ions. Because if you have absolutely pure water, if this splits, it's going to split into hydrogen ions and hydroxide ions. Because all you have is H2O. Well, H2, two H's and an O, and the plus and minus cancel. Okay, this becomes this. Okay, so if you have absolutely pure water, you have exactly equal concentrations of hydrogen ions and hydroxide ions. Now, if you add certain things to water, which are called acids and bases, what they do is they change the concentration of hydrogen ions and hydroxide ions. And we care that it's going to change the concentration of these things, hydrogen ions and hydroxide ions. Okay, why do we care? Because it can drastically affect the chemistry of your cells. Like, if you think about it, when most people think about an acid, they think about something that if you get it on your skin, it's going to dissolve your skin. Okay, so like a strong acid, yes, can dissolve your skin. Your skin is made up of skin cells, so obviously that acid is drastically affecting or changing the way that cell behaves. Okay, so what exactly is an acid? An acid is any substance that increases the hydrogen ion concentration of a solution. In other words, when acids dissolve in water, they release hydrogen ions. So that's what an acid is. An acid is anything that gives away hydrogen ions. Acids give away hydrogen ions, because that's what an acid is, anything that gives away hydrogen ions. So what is a base? A base is the opposite. A base is any substance that reduces the hydrogen ion concentration. In other words, bases take hydrogen ions. So acids give away hydrogen ions, bases take hydrogen ions. Acids give away hydrogen ions, bases take hydrogen ions. That's what acids and bases are. And like I said, we care about how acid-like or base-like something is because it's going to drastically change the chemistry of our cells. And we have a way of measuring how acid-like or base-like something is. It's called the pH scale. So what is the pH scale? Okay, well, pH is the negative logarithm of the molar concentration of hydrogen ions. Okay, so pH is the negative log of the molar concentration of hydrogen ions. Now, before you start to freak out, let me slow down and back up first. If you see this symbol in science, like biology or chemistry, it means concentration. Okay, a number in a certain size space. And I taught you earlier the way we measure concentration is molar. So if I have H plus inside it, what that means is a molar concentration of hydrogen ions. Let's say I told you that some solution has a molar concentration of hydrogen ions of 10 to the negative 7th molar. And I ask you to calculate pH. What you're going to do is you're going to take out your calculator and you're going to take the negative log of 10 to the minus 7. Okay, and then your calculator will tell you the answer to that. And that's how you're going to solve any pH problems that are going to be on Mastering Biology. Is you're going to use your calculator and take a negative log of 10 to the negative 7th. But there might be times where you have to calculate pH without using a calculator. And you might be like, what the hell? I can't calculate negative log in my head. Frankly, I don't even know what negative log really means. Okay, well, don't freak out. There's actually a cheat sheet way of doing it. So let's say I tell you that the hydrogen ion concentration is 10 to negative 6th molar. And I ask you, okay, what is the pH? In that case, the pH is just 6. Whatever this exponent is, that's the pH. The exponent will always be a negative number, but the pH will always be a positive number. If I said the molar concentration of hydrogen ions was 10 to the negative 2 molar, then the pH is just 2. If I said the molar concentration of hydrogen ions is 10 to the negative 12 molar, then the pH is just 12. So that's the cheat sheet way of doing it. Now, sometimes you can do it that cheat sheet method, and sometimes you can't. Why is that? Like, why are there times where you would have to use a calculator? Okay, well, this number here, like 10 to the negative 7th, okay, that's a shorthand. What that really means is 1 times 10 raised to the negative 7th power. let's say instead you're given something like, let's say 2.6 times 10 to the negative 7. In that case, the pH is not 7. What you have to do is you have to do the negative log of this using a calculator, and then that will tell you the pH. Okay, so if you're given nice whole round numbers, you know, like this, you can just use the cheat sheet method. If you're given something like this, 2.6 times 10 to the negative 7, then you'd have to actually use a calculator and do negative log. Now, if you're doing like your homework and you need a scientific calculator, if you have a graphing calculator, that works great. If you have a scientific calculator, that works great. If you got a smartphone, open up your calculator app and turn your phone sideways, and it should turn into a scientific calculator. Or open up Google and Google like scientific calculator, and a web-based scientific calculator will open up for you. So everyone has access to some type of scientific calculator when you're doing like the homework. Now, another thing to be careful of, besides making sure this is like a nice round number, not like, you know, 2.6 times 10 to the negative 7. The other thing to keep aware of is negative log is referring to the molar concentration of hydrogen ions. So let's say I said that the molar concentration of hydroxide ions is 10 to the negative 6. In that case, pH is not 6. Because pH is talking about hydrogen ion concentration, not hydroxide ion concentration. However, the two are related to each other. And it's actually pretty easy to calculate, again, as long as it's nice whole round numbers. So if I tell you the hydroxide ion concentration is 10 to the negative 6, then the hydrogen ion concentration would have to be 10 to the negative 8. These two exponents have to add up to negative 14. And then the pH would just be 8. If I said that this was 10 to the negative 2, then this would be 10 to the negative 12. The pH would be 12. These two always add up to negative 14, but the pH is based upon this one, not on this one. So pH is based upon hydrogen ion concentration, not hydroxide ion concentration. Okay, so here is the pH scale. The pH scale goes from 0 to 14. There's nothing less than 0, nothing more than 14. Numbers smaller than 7, those are acids. Numbers bigger than 7, those are bases. Exactly 7. Okay, that is not an acid or base, it's neutral, like pure water, H2O and nothing else, pure, absolutely pure water. That's pH of 7, that's a neutral solution. Alright, so some examples. Let's do acids first. Example of acids you might have interacted with, like maybe you drank today. Coffee is an acid, it's a pH of 5. Okay. Something that's even more acidic that you could have drank is soda, like Coca-Cola. Okay, it's a pH of 3. That's actually a pretty strong acid. If you've never seen or done this before, get a Coke and drop a penny in it and leave the penny there for a few days. And what's going to happen is the Coke is going to dissolve that penny. So that Coke that you're drinking is a strong enough acid to dissolve a penny. Now, you know, some might start freaking out. Why am I drinking something that can dissolve a penny? Now, I'm not saying that Coke is good for you, but once it gets to your stomach, the fact that it's an acid is not something to worry about because your stomach is filled with stomach acids, which are an even stronger acid. Okay, now it can like erode your teeth, okay, but once it gets to your stomach, the fact that it's an acid isn't that big a deal. Okay, and then acids are stronger than that, like battery acids you don't want to drink. All right, now how about bases? Okay, something that's just very weakly basic, a tiny bit of a base, is the oceans. The oceans are slightly basic, around pH of 8. Another base you might have interacted, maybe you've drank before, is milk of magnesia. Okay, so this is something that you take, or you can take, if you have an upset stomach. Like you can buy it from like Publix or CVS, and it's a base. So why, you might think to yourself, why am I drinking a base? Well, the reason that you might be drinking a base like milk of magnesia is because there might be times where your stomach is upset because you have too much stomach acid built up. And then you drink this base, milk of magnesia, and what it does is it cancels out that acid. When you combine acids and bases together, they cancel each other out, and it can make your stomach feel better. Okay, so that's a base you've interacted with that you might have drunk before. Now, stronger bases, you do not want to drink. They're things you use to clean your house. Like ammonia is a strong base. Bleach is a very strong base. Oven cleaner is an even stronger base. All right, those are some examples of acids and bases. And like I said, absolutely pure water is not an acid or a base. It's neutral. So neutral means it has exactly equal concentration of hydrogen ions and hydroxide ions. Now remember what an acid is. An acid is anything that gives away hydrogen ions. So an acid will have more hydrogen ions than hydroxide ions. That's what an acid is, something that gives away hydrogen ions when you put it in a solution. Remember what a base is anything that takes hydrogen ions. So a base will have less hydrogen ions than hydroxide ions. Okay, so those are acids and bases and the pH scale. Related to acids and bases, there are also things called buffers. What a buffer does is it helps to maintain a certain pH. In other words, if you add an acid or a base to a buffer, the pH doesn't really change. For example, your bloodstream, okay, your blood. Your blood needs to be at a certain pH. I can't remember exactly, but I think it's like 7.4 or 7.6. Okay, and it needs to be that pH. It can vary just a tiny, tiny bit. But if it changes to like 7 or 8, or 6 or 9, you can get really sick. Okay, so you need your blood to be at a certain pH. Well, how does your body maintain your blood pH? Well, it turns out that you have inside your blood a buffer. And what that buffer does is it resists changes in pH. Like, for example, let's say I have a beaker that's filled with water. Okay, and then I add some acid to that beaker. Okay, so some acid I'm adding to this beaker. What's going to happen is the pH of that beaker of water, the water pH is going to very quickly drop. It's going to change the pH very fast. Now, let's say instead I have a beaker, which for some reason this time I have a beaker filled with your blood. Okay, I don't know why, I guess because I'm a psychopath. I have a beaker filled with your blood. And then, now I take an acid and add it to this beaker of your blood. What's going to happen? The pH is not really going to change. Okay, why? Because your blood has inside it a buffer that resists changes in pH. If you add an acid, the pH is not going to really change. If you add a base, the pH is not really going to change. Okay, so what a buffer is it is a weak acid and a weak base mixed together. So if you add some base, okay, then the acid cancels out that base. If you add some acid, then the base cancels out that acid. Okay, so that's what a buffer is. Now, since we're talking about acids and bases, and we're talking about water, and we're talking about biology, the study of living things, okay, a brief thing to mention is something that we as humans are doing. We as humans are burning a lot of fossil fuels. And when we burn fossil fuels, we release things into the environment. For example, carbon dioxide. And those molecules that we're creating, carbon dioxide, by burning the fossil fuels, they have to go somewhere. Where a lot of that carbon dioxide ends up going is into the oceans. Okay. Well, when carbon dioxide combines with water through a long series of complicated chemical reactions, you don't really need to worry about. What happens is it starts to acidify the ocean water. So by burning fossil fuels, what we're doing is we're making the ocean more acidic than it should be. And there are organisms that are living in the ocean. And they need that water they're living in to be at a certain pH. Just like you need your blood to be at a certain pH, these organisms that are living in the ocean need the ocean water to be at a certain pH. This is a coral reef as it used to look. This is that coral reef as it looks today. Okay, what's happening is we've started to acidify our oceans, make them more acid-like than they should be, and some of these organisms cannot handle those more acidic conditions, just like you couldn't handle if your blood pH changed. Now, when we burn fossil fuels, Besides releasing carbon dioxide, we also release other things like sulfur oxides and nitrogen oxides. These molecules combine with water in the air, okay, and they make it more acidic. And then that more acidic water comes back to the earth, as you might have heard of before, acid rain. Okay, and this more acidic water then combines with things like the soil and the streams and the lakes. And there are organisms that are trying to live there, and again, they can't handle those changes in those acidic conditions. Okay, so that was a really, really brief introduction to what's happening when we're burning fossil fuels. Now, if you want to learn more details about that, take environmental science. In environmental science, they can talk about topics such as that. Okay, but that was your introduction to water and acids and bases. Okay, and that is Chapter 3. So until next time, this has been Dr. Sage.